In our last part, we're going to be talking about the shape of the universe. And this is a recurring theme across the sciences that shape or the form can determine function. And in our discussion of the fate, we're going to say that where the matter is in the universe and how much there is will determine its ultimate fate. And I feel like this image here very much encapsulates some of these concepts we're going to talk about. Because here you have this volcano that has a very volcano shape to it. And yet, when you look at the shadow that's projected by it, it almost looks like a pyramid. And this is just a combination of our perspective, us the viewer and the camera, our perspective, the curvature of the Earth, and the angle of the light coming in and landing on that volcano. And yet, you can see the different shapes being mixed together. And I feel like this very much captures the essence of trying to observe something and figure out what is it that we're seeing and understand what's the big picture. So the shape is correlated to basically the fate of the universe, what's going to happen to it. And so let's just stop here and ask ourselves right now, to the best of our knowledge, what do we know is going to be the final state of the universe? How is matter going to be distributed through the cosmos? And we'll go through the options. You could have what's called a big crunch, where the universe has blown up in size and gravity takes over and crushes it back into a new singularity. There could be an ever-expanding universe that just keeps growing in size, and in the end you'll have just hydrogen and helium gas sprinkled throughout the cosmos. Our third option is that the universe will have grown until eventually it just reaches a steady state where it stops expanding. It's no longer changing size, none of this, it's just steady. And then over the eons, the only thing that will be left will be the longest living objects, the white dwarfs, neutron stars, and mostly black holes. Our next option will be this ever-expanding universe, but instead of being hydrogen and helium gas, it'll just be photons and some elementary particles. Everything else will have broken apart, crumbled away. And our final option will be just this basically wide network of black holes. Everything has either fallen into them or compressed into its own black hole. So pause, think for a moment, get your answer together. And I'll say that to the best of our knowledge, this is the fate of the universe. It's going to keep expanding forever and ever. And over time, everything's going to just start slowly breaking apart into the constituent components until the only thing left is this sea of low energy photons and maybe some stray particles, elementary particles that can come out of the vacuum state and go away. And that's going to be it. All the galaxies, even the black holes, all of that will eventually just disperse. So we're going to be talking about this cosmology. And this is basically the study of the development of the universe. And if you go online, search, there's a lot of different ways to define what we mean by cosmology. So for the purposes of this part, I'm going to go with cosmology is just trying to study the nature of the universe in terms of how it got to the state it's in now and what will be its eventual final states. And that's how I'm going to go with my definition of cosmology. There's a lot of different, they all are themes, variations of this. Basically, it's trying to study the big picture. So, emphasis here is that we know now that the universe is expanding. We look across the cosmos, we see that galactic redshift. And one question is basically, what will the expansion be like in the future? What was it like in the past? What will it be like in the future? And the biggest determiner of this factor is, we're on brand here. Remember we talked about the stars. What's the number one factor in the fate of the stars? Well, how massive they are. What's the number one determiner of the fate of the universe? It's going to be related. It's about the amount of matter and energy in the universe that will determine the ultimate expansion rate and its ultimate fate. How much stuff is here. And I do need a caveat here. I need to say there is matter, the stuff we're composed of, and energy. How much energy is just prevalent. Right? This distinction isn't very important now, but it will come up later. So, a couple of things we need to define. First off, we need to define just this rho, and that is going to be the density of the universe, the ratio of the amount of mass over the volume of the universe. This is a thing that we're trying to measure. We have ideas, pretty good ideas, but this thing is up to how much can we find. Then we're going to find this thing called this rho C, this critical density. This is going to be absolutely important for us because what happens in the universe will depend on what the actual density of the universe is over this critical density. Now, astronomers, cosmologists, they've shortcutted and they've defined this omega m, and they call it the density parameter. So omega m is the ratio of the actual density of the universe over this critical density. And I'll get to why we call this the critical density in a little bit. But first, we're going to put on our physics caps here, and we're going to ask ourselves, what are the units of this density parameter? What's the units of omega m? All right, pause the video, try and work it out, go back to the last slide, look at the equation. When we're talking about physics, we're always trying to figure out, what am I measuring? And that means, what are the units of it? If it's a distance, am I measuring feet, meters, centimeters? Is it a speed? Is it pressure? What are we measuring here? So, pause, come back. All right, let's work this out together. All right, so let me pull up my little drawing tool. Let's do it. Let's do it in red. All right, so omega. It is the ratio of the density of the universe over this critical density. Now, I know some of you probably just jumped right to the answer, but I want to go over in detail for those who are struggling with what I'm asking or what the heck to do. So what I'm asking is, what are the units? Well, density. Density is a mass per unit volume. How much stuff, how much mass is in a given set of it. So that's going to be a kilogram per cubic meter. Think about taking a box and filling it with water. How massive is that? Critical density, same thing. That's also a kilogram per cubic meter. All right. Well, the kilograms will cancel out. The cubic meters cancel out. And so this density parameter 1, in terms of units 1, which is another way of saying that it is dimensionless. It actually has no units. And this is the shortcut. Instead of saying, well, is it 10 million atoms per cubic meter, or is it 0.001 atoms per cubic centimeter? Like, instead of worrying about the actual values of the densities, we've shortcutted by defining the density parameter. So now I'm going to go through and talk about what are the range of possible values for this density parameter and what that means for the universe. So what I have here now is a number scale, all right? We can go from 0 to anything greater than 1, and that's going to be our density parameter. And critical values. If the density parameter is equal to 1, exactly 1, the universe expansion stops. And that goes back to what I mean by that critical density. If the density of the actual universe over this critical density are equal, the universe will have reached a final state and stop expanding. And you're going to hear me repeat all this multiple times, I promise. All right. If the density parameter is less than 1, then the expansion rate of the universe will just keep going up, keep blowing up, keep going out there, and accelerate. If the expansion rate is greater than 1, then that means that the amount of material here is greater than that critical amount. And what will eventually happen is that gravity takes over and crushes things back into itself. So basically, steady state, critical value if you're 1. Anything to the left, you keep blowing up. Anything to the right, and you eventually crush back down. So now what I'm going to do is I'm going to zoom in here. Just zoom into that little slice there. And this is where we're at. This is where we're at right now. The accepted value for the density parameter is about 1.02 plus or minus a little bit. Plus or minus. And of course, yes, our plus or minus literally does span the entire scale. So this is like the cosmologist's goal, to narrow down precisely what is the exact value of the density parameter. Right now, the accepted value is that it's going to fall probably exactly on 1 is the accepted notion. But we've got some error bars here. There's some uncertainty. So what we really want to do is keep studying the universe and focus this in. Get those error bars smaller and get a more accurate, precise measurement so that we can really predict what's going to happen to the universe. So I'm going to repeat all this, but have some diagrams to go with it now to help you visualize what I mean by the expansion of the universe. So a different way of plotting this, we're going to look at time versus what's called a scale factor. Basically, how big the universe is and how quickly it's growing in size. And we'll go through this again. If the density parameter is less than 1, then the universe just keeps to continue expanding. As time goes on, the scale factor, the size of the universe, just keeps getting bigger and bigger. So you've got the Big Bang, big expansion outwards, and as time goes on, space-time itself will keep growing in size, and it will continue to do so, never stopping. If we are at that critical density, then we'll say is there was a Big Bang, universe is expanding outwards, but as time goes on, the scale factor, the size of the universe, will eventually, let's use this color, will eventually reach an asymptote. It'll eventually stop growing in size. You can see this with the orange arrows, that as the universe gets bigger and bigger, the rate at which it's getting bigger slows down and eventually stops. And then you'll just have this massive universe that's static now. And then finally, if the density parameter is greater than 1, what happens? You've got the Big Bang, the universe blew up in size, expanded, reaches an inflection point, that'd be about here, and then gravity finally gets to dominate, take over, and crushes back down into a new singularity. So it is absolutely crucial that we figure out what the density parameter is, because the different fates of the universe, what ultimately happens to us, is fundamentally determined by this ratio, by this omega m. So let's go into a little bit of details now. Let me pull back from that drawer, your brain space, when I said, hey, this is the combination of matter and energy. Why did I make that distinction? Well, we've talked about ordinary, our luminous matter, and our dark matter, and we count up the stars, count up the galaxy, and we look at the size of the universe, and we get that the ordinary matter, stars, the gas, the dust, you and me, we make up about 0.02 for this density parameter. So this thing needs to be exactly 1 for a steady state universe, and we are 0.02 of it. Alright, well, there's a lot of this dark matter out there, and We don't have a precise figure because we still don't quite know what that dark matter is, but based on the rotation rates of these galaxies and the gravitational lensing effects, we've got a pretty good idea that dark matter is about 0.3. Well, didn't I just say a few slides ago that the density parameter is like 1 plus or minus a little bit? We are far cry short of this. We're basically missing 0.7 of this density parameter. What gives? How can I say that this parameter is 1 when all the matter of the universe is only 30% of that? What's going on? What are we missing here? Well, I'm going to go on a little bit of a sidebar here. All right. We're going to do this little recap. I'm going to say, remember, Einstein's theory of general relativity. It says that if you've got mass, there's gravitational attraction. And straightforward application of that. Imagine this was the universe before the Big Bang. All this energy compressed together. You can think of it as being a bungee jumper on a big spring. So after the Big Bang happens, that releases the energy. And the universe explodes forward and just keeps expanding. But eventually that spring will reach its limit, stretch. It can't stretch anymore. And what we expect from just gravity alone is that, well, it'll retract. That the bungee jumper or spring jumper on this figure, the bungee jumper will start to collapse, return back. So relativity by itself, we would predict a collapsing universe. And our values for that critical density parameter don't even agree with that. And then we say, well, what do we observe? Well, we observe a universe that has exploded forth, and not only is it getting bigger, the rate that it's getting bigger at is increasing, the expansion rate. So the rate that things are going away from us is going faster and faster. What are these discrepancies? What's going on here? Could the expansion rate of the universe change throughout time? And so, simple measurement, simple experiment. We're going to try and measure the distances using two techniques. This is a very common trick that scientists use. I'm going to measure the exact same thing twice, but using different tools. I'll use one trick, I'll use another, and I'll say, do they agree? So here's the trick that we're going to use. We're going to try and get the furthest distances out there using the tools we've used before, the type 1A supernova. All right, you get the luminosity, and through that mechanism, you get the distance. Then we could say, well, let's look at this galactic redshift. I've been repeating over and over again that the further away in the cosmos something is, the higher the redshift. So that redshift value is another tool that effectively tells us the distance to that object. And now let's compare. And it turns out that the values don't really agree. When you look at today, they're pretty much one-on-one. The redshift versus distance measurements, they tend to agree. But as we go to higher, as we look further away, we look at this plot of the brightness, basically telling us the distance, and the redshift. We notice that these lines don't line up. They're not one-to-one to each other. Another way to say this is that we've looked at distance, the faraway supernovas, and they are dimmer than what certain tools would let us to predict. So one way to understand this is that the rate that the universe is expanding has changed. Not only is the universe expanding, but it's increasing, getting faster. So this is actually, I've said this over and over again throughout these lectures, but now we're looking at the very first pieces of evidence that the universe expansion rate is accelerating. We are getting further away from each other, and the pace, the acceleration of that change is changing. Well, the only way for that to happen is if there's a force pushing. There has to be something pushing on you. Imagine you're in a car. You're going 30 miles per hour, and you want to go faster. What do you need to do? You put your foot on the accelerator, and you speed up. You are using energy to create a force in the engine to increase your speed. So, what's the cosmological equivalent? Universe could be expanding, but everything's just going at a constant rate. But it's not only is it what we see is that it's going away, and it's going away faster and faster. In fact, the further away it is, the greater its rate it is getting away from us. So, what's the cosmological gas pedal? What is driving the universe, causing it to expand further and further out? Another way to phrase this, what is the anti-gravity? Gravity should be taking everything, slowing it down. Gravity should be the brakes of the universe, bringing things back down. And yet we see the accelerator on the gas pedal. We see the universe is blowing up. And so, this is what we dub this dark energy. We observe. There is no dispute here. We look at the cosmos, we see things getting away from us, and we have to build our ideas, our knowledge based on the evidence. And the evidence says the universe is blowing up at a faster and faster rate. Well, the only way for that to happen is if something's there pushing it. Something is driving the universe apart. So we've detected this, we know it must exist, and that's what we've dubbed this dark energy. Told you I'd get to the distinction between dark matter and dark energy. Dark matter explains the mass of the galaxies and how the galaxy clusters are forming. Dark energy says, why is the universe getting bigger and bigger? We know it's happening. We look across the cosmos. We see it's getting bigger. And so now we have this dark energy term. And this adds to our density parameter, because when I said at the beginning, the density parameter is the combination of the amount of mass and the amount of energy in the universe. And now we have indisputable evidence that there is another force, or this anti-gravity thing. There is dark energy out there pushing the universe to be bigger and bigger. And I'll skip the value. Our best estimates have put this, we call it omega lambda for the dark energy. Our best estimates have put that at around 0.7. And yes, I'm cutting off all the digits here. So now we need to account not only for the amount of mass, but the amount of energy, and try and stick things together. And like I said, we discovered this by looking at measuring distances using supernova or redshift. So there are different ways for us to try and put limits on what are the available values. So you're looking at these ratios of the density parameter based on the mass, the density parameter based on the energy, and where we fall on this, right? These are different experiments trying to constrain both values. Ways you can do this, way you can put limits on what the allowable values are, is basically say, well, what are the supernovas? You measure supernovas across all the galaxies. Another tool will be our cosmic microwave background. Another tool, you say, here's a bunch of galaxies, here's a bunch of galaxies, and you start stitching them together, and you get this combination of what's that amount of dark matter, and the amount of dark energy present. So stitching, plotting all these together, that's how we got to our value of about 1 plus or minus a little bit for that overall density parameter. Whereas the mass of the universe is about 30% and the energy is about 70%. Here's another way to visualize this. We'll look at the composition of the universe. What's the universe composed of? Protons, electrons, the atoms that you and I are composed of, the things that we will spend our entire lives trying to study and comprehend. All the atoms, every chemical interaction, every molecule, every piece of food you consume, all of that is less than 5% of the universe. Everything that we're standing on right now is only 5% of the universe, and that's an overestimate. Then you add in that dark matter. We know it's there. We see its gravitational effects. And that's only about a quarter of the universe. So there is this prevalent energy throughout throughout the cosmos that's driving the expansion, blowing the universe up in size. And that's somewhere of 70% of what exists out there. So stitching this all together, the big takeaway from this, 95% of the universe is stuff that we know it exists. We know that stuff exists. We've seen its consequences. We see its effects. But we don't know what it is. And I just find that to be absolutely amazing. We know about how much stuff is out there in the universe, and yet we still can't give you a definitive answer. What is dark energy? We know it's there. We know there is this anti-gravity force that's pushing the universe to be bigger and bigger, but we don't know what's the source of it. We don't know what's causing it. Similar issue with the dark matter. We know it's there. We've detected it. It must be there. But is it this strange, exotic, cosmic particle we've never detected? Is it just a bunch of floating Jupiters that are cold and dark? We're still not certain. And so I absolutely love the fact that there is so much of this universe that we still do not comprehend, which means there's so much for us to still learn about. So to wrap these up, summarize things, galaxies and universe are clustered together, and they tend to make these filament structures. And that's due to the prevalence of dark matter. Dark matter's presence at the beginning of the universe was crucial in determining what the shape of the universe is. These bands, these filaments, are tracing patterns of dark matter throughout the cosmos. And trying to find the exact amount of matter and energy in the universe is absolutely crucial to understanding what is the final shape of the universe. What is the universe going to look like? So, we'll call it into section 21. See you all next time.